But before we get into question 10.8, I want to remind you about the tetrahedral shapes around the central atoms in these two molecules that we looked at the last class. We looked at ethane and ethanol, and I actually showed you the models of these molecules. And so we have more than one central atom in these molecules. And we looked at the geometries or the molecular geometries of all of the central atoms, whether they were carbons, the two carbons in ethane, or the two carbons and the oxygen in ethanol. Well, with that in mind, let's try a practice problem, which is problem 10.8. It says you're predicting molecular shapes when we have more than one central atom. Determine the shape around each central atom in acetone. Now, this is kind of an interesting way to present a molecular formula here, but the reason they have these two CH3s in these brackets with the 2 by it is so that you know that there's two CH3s and that those carbons are attached to 3 hydrogens. So what does that tell us? That tells us that we've got a carbon, okay, attached to an oxygen, and then that's attached to 2 carbons that have 1, 2, 3 hydrogens attached to them like this. Now, you notice that I'm kind of doing things in a little bit different order than I usually do. Normally, I get my students to tally up the total number of electrons. So we could do that now. We've got 3 carbons, and there's 4 valence electrons in a carbon, so 3 times 4. We've got a total of 6 hydrogens, so that's 6. And then we've got 1 oxygen, and oxygen has 6 valence electrons. So that's 4 times 3, which is 12. And 12 plus 6 plus 6 is 24 electrons. How many electrons have we used up thus far? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I've used up 18 electrons. That means I've got 6 electrons left. Could anybody suggest to me where I should put those remaining 6 electrons? Yeah, somebody says oxygen. That's true. Is there so I think the reason my students are all saying oxygen, yeah, is because the oxygen is lacking an octet. Matthew says the carbon and the oxygen. Why, Matthew? Because Matthew recognized that not only is the oxygen lacking an octet, the carbon is also lacking an octet. He also probably remembered that carbon always has 4 bonds, right? So if we put a second bond here, and oxygen always has 2 bonds and 2 lone pairs, like that. And so that is the Lewis structure for my molecule. This molecule is called acetone. If you've ever been to the paint section in Home Depot or Lowe's, you might have bought some acetone, or if you've ever used nail polish remover, you'll know that it's mostly made of acetone. Now, before we draw this molecule with the correct molecular geometry, I want you to think about the number of regions of electron density there are around this central carbon. Could anybody tell me how many regions of electron density there are around this carbon that I have the red arrow by? Yes, exactly. There are 3, right? Because it counts as 1. So we have 1 double bond and 2 single bonds. So that means we've got a total of 3 regions of electron density, and there's no lone pairs. That tells us that that carbon must be trigonal, planar. Okay. Now, what about the 2 carbons? I'll just draw an arrow by, I don't know, by this one. How many regions of electron density are around this carbon? And it's the same for both. Yes, exactly. There are 4 regions of electron density. 4 regions of electron density, and none of them are lone pairs. And so the molecular geometry around both of those carbons that are on the end is tetrahedral. Now we can draw the molecule with the correct molecular geometry. Let me show you how you do that. We'll start with our central carbon, put in our double bond oxygen, and then we'll put our 2 bonds to the 2 other carbons. Now these carbons are tetrahedra. And so I'm going to draw the bonds to this hydrogen in the plane of the board, and then I'm going to draw 1 hydrogen going in the back and 1 hydrogen coming out in front. A hydrogen going in back and a hydrogen going out in front like this. What about bond angles? The bond angles in the trigonal planar are going to be, if you just write around 120. Now, I'm sure some of you are thinking, well, here I have a double bond, so it's going to repel, this group. Well, even if you just put close to 120, that works for me. So all of these bond angles here are going to be at close to 120. The other bond angles shown here in the tetrahedron, these, as long as you put, they're close to 109.5 degrees. That's good enough for this guy. Okay, all these bond angles, they're all close to 109.5 degrees. Let me show you what that molecule looks like. And here it is. This is, a three-dimensional model. You can see the carbon doubly bound to the oxygen. I don't have lone pairs in here, but you can imagine them in here. And then I have my two CH3s. Again, you can see the bond angle between the double bond and the single bond between the carbon and carbon here. You can see that these are all around 120. And you can see that the bond angles here on the CH3s, okay, or this bond angle here even, those are all 109.5. So there's my model of acetone. And we were able to figure out the Lewis structure and the molecular geometry at all three of the central atoms. 2 carbons on the sides and this 1 carbon in the center. Now we're going to move on to the last section of chapter 10, which deals with molecular shape and molecular polarity. In order for you to master section 10.3, and I know I'm repeating myself because I said something very similar the last 2 lectures, is that in order for you to understand molecular polarity, which is what we're getting at in this section, you have to understand molecular shape, which is molecular geometry. In order for you to understand molecular geometry, molecular shape, you have to understand Lewis structures. And thus you can see that this chapter is extremely additive. It is extremely content driven. You have to understand the first part to get to the next part, so on and so forth. Let's take a look. Overall, molecular polarity depends on both shape of a molecule and bond polarities. The polarity of a molecule is measured by its dipole, the abbreviation mu, that's the Greek letter mu, so mu, which is given by the unit debye. We're never going to really concern ourselves with the units of debye a whole lot in this class, but they are the units that are used to measure the overall dipole moment of a molecule. A molecule is going to be polar if it contains one or more polar bonds, but the individual bond dipoles do not cancel. So what does that mean? That means that bond dipoles are going to cancel from time to time, and we're going to see several examples of that. Here's an example, carbon dioxide. The difference in electronegativity between carbon and oxygen makes these bonds polar, right? We said that if the difference in electronegativity between 2 atoms fell between 0.4 and 1.7, the bond was a polar covalent bond, right? How do we calculate the difference in electronegativity? Delta En is going to be equal to 3.5 minus 2.5, which is 1.0. So we have a polar covalent bond. If we draw the Lewis structure of CO2, which is shown down here, okay, there is a difference in electronegativity, again, between those 2 elements. Yes, oxygen is more electronegative than carbon. Therefore, we're going to draw the dipole going in the direction of the oxygen. So this is a polar bond. This is a polar covalent bond. No argument there. But this is also a polar covalent bond on this side for the exact same reasons. And it's pulling in the exact opposite directions, or direction. Why? Because the geometry of this molecule, the molecular geometry, is linear. So it's like a tug of war with equal forces being pulled in equal and opposite directions. Therefore, the dipoles cancel. So the take-home message from carbon dioxide is that yes, there are two beautiful polar bonds in carbon dioxide, but overall the molecule has no net dipole moment. Its dipole moment measures as 0 dBi. No dipole moment whatsoever. Give me a thumbs up if you follow me on the rationale for that. Okay, let's look at another example. Let's talk about bond polarity in water. We've looked at the Lewis structure of water earlier on in this class. We discussed the molecular geometry and the electron geometry. I'll just refresh your memory very quickly that water has this bent shape like this. Yes, I know, I'm fully aware that the electron geometry is tetrahedral, but the molecular geometry is bent. So this bond angle is less than 109.5 degrees, like that. Are there polar bonds in water? Absolutely there are. The difference in electronegativity between hydrogen and oxygen, 3.5 minus 2.1 is 1.4. That's a pretty polar bond. Okay, so we have two polar bonds in a water molecule. But if we take a look at them, you can see that one of them is going in this direction, and the other one is going in this direction like this. Water has that bent geometry, and the individual bond polarities do not cancel each other out. They're not pointing in the same direction. They're not pointing away from each other in opposite directions. This molecule has an overall molecular polarity. The oxygen is partially negative, while the hydrogen atoms are partially positive. If I add up these two arrows, okay, if I have two cars that are heading towards each other, maybe I won't use a highlighter. If I have two cars that are heading towards each other at an intersection and they collide in some kind of crash, are they going to stop dead in their tracks? No, they're going to move in this direction a little bit, right? So you have to be able to add these vectors in your mind and say, well, if I add those two vectors, overall, I'm going to get a resultant vector, which is in this direction. And so that is why we draw the dipole going in this direction. So water is a polar molecule. It's got two polar bonds. They don't cancel out. And if you add up those two dipoles, they point in this direction of the big green arrow that I've drawn, or the one that's in the green circle. If you look at an electrostatic potential map, which is what this is here, which shows where most of the electron density is, the red color denotes more electron density. And you can see that there's much more electron density by the oxygen, right, than there is by the hydrogen, which are delta positive. Give me a thumbs up if you follow me on that water is a polar molecule. Good, good. Okay. Well, with that in mind, let's take a look at a couple more examples. We're going to compare these two molecules. The molecule on the top is CCl4, and this molecule is CHCl3. Both of these molecules have the exact same shape. They both have a tetrahedral molecular geometry. But the difference is that they have very different polarities. The first molecule, which is carbon tetrachloride, CCl4, is nonpolar. Why? Because even though chlorine is more electronegative than carbon, so there is a dipole. There are in fact 4 dipoles that are all going in equal and opposite directions. So since they're all pulling in equal and opposite directions, they cancel each other out, and carbon tetrachloride is going to be nonpolar. Whereas when I have this molecule, CHCl3, which is chloroform, the dipole between the hydrogen and the carbon goes in this direction. So if you tally up all 4 of these dipoles, they're all pointing down. And so the net dipole is going to be in this direction. Give me a thumbs up if you can add those dipoles together in your mind to get a resultant vector. imagine that this is your CCl4 molecule. Okay, imagine that these aren't hydrogens. Imagine they're chlorines. You have a dipole going here, 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 and here. They're all pulling on the molecule in equal and opposite directions, right? And so there's going to be no overall dipole. They're all going to cancel out. If I replace one of those atoms with a different atom, so imagine that this green one is a hydrogen. Now this dipole between the green and the black is going in this direction, and all of these ones are going down in this direction. So overall, the dipole is going to be going down like that. This is one of those examples where molecular models come in really handy. Give me a thumbs up if the models help at all. Anyone? You know, they say a picture is worth 1,000 words, so maybe models will help us a little bit. All right, good. Any questions about that? Trying to find out where I was in my slides. There we go. Well, now that we've looked at some examples, let's try an example as a group. There's a big difference between seeing a solution and understanding it, you know, or seeing a solution worked out in front of your eyes. They usually make sense to students. There's a big difference between that and being able to do the problem yourself. This question says, for each of the following molecules, use the molecular shape and electronegativity values and trends to predict the direction of the bond and molecular polarity if present. Well, let's give it the old college try. First, we'll start with ammonia, NH3. Aaron, I'm not sure if I understand your question. You say, but none of them are directly opposite one another. They're not directly opposite each other like they would be in linear, but since all of the bond angles are identical in the tetrahedron, they're all 109.5, right? They're all at equal and opposite points, if you will, of the tetrahedron. And so they're all going to cancel each other out.
Okay, that makes sense. Thank you.
No problem. Okay, so let's start with ammonia. I'm not going to spend a lot of time on Lewis structures anymore because we've spent enough time on those already. So by now, you should be able to draw the Lewis structure of ammonia, NH3. There's our Lewis structure, done. We've got 4 regions of electron density. One of them is a lone pair. So this is a trigonal pyramidal structure. We'll draw something that looks like this, and we'll draw this hydrogen coming out like this. Now, if we look at the electronegativity of hydrogen, it's 2.1. The electronegativity of nitrogen is 3.0. And therefore, the dipoles are going to be going in this direction, towards the nitrogen. Okay, they're all going to be climbing up that hill towards that nitrogen. So that means that overall, the resultant dipole is going to be, they're not going to cancel. Also, there's one thing I want to point out to you. I don't know if it's in our book or not. I can't remember. But there is a dipole between an atom and the lone pair, okay? It's going to be a small dipole, but there's always going to be a dipole pointing towards the lone pair like that. Small one, but there's going to be one nonetheless. So my question to you is, and it's not easy to do this over Microsoft Teams, but I'll just throw it out there. Could anybody tell me what direction the overall or the net dipole would be pointing for this molecule? Would it be left, right, up, down? Yes, based on the way that I have it drawn on the page. Okay, you can turn the molecule upside down if you want. But what Blake is saying is, with respect to the way that I have it drawn literally on this piece of paper or on my iPad screen, the resultant dipole is going up. So this is a polar molecule. Okay, so this is the direction of the dipole, like this. If you don't follow me, let us take a look at another model. Here's my NH3 molecule. Oops, I pulled off the wrong atom. There we go. So we have our nitrogen. Just imagine this black sphere is our nitrogen. We have our 3 hydrogens. All of these dipoles are going in this direction, right? They're all climbing up a hill. And then you have a dipole going up like this. So overall, the dipole is pointing up. When you add all four of those vectors together, they're pointing up like that. Give me a thumbs up if you follow me on up. It's not much to be following me on, but if you follow me on up, the up direction, or even that it's just a polar molecule. Okay, good. Let's try the next one, boron trifluoride. Hey, you know what? I don't do this kind of thing a lot with my students. I don't give a ton of really challenging questions in lecture. I don't dig that a ton. But could anybody answer BF3 right away and tell me whether the molecule is polar or not? I know it's a big question without us maybe going over it. But is anybody able to solve that in their head? Because we have looked at the Lewis structure. Okay, I got somebody saying polar, yes. Does anybody else say polar, non-polar? What other kind of votes do we have here? BF3. Okay, we've only got a couple of votes. Let's take a look at it. You remember that boron is found in group 3A. So boron is one of those exceptions like beryllium where it's electron deficient. Boron only forms 3 bonds. So if we draw the Lewis structure of BF3, all of the fluorines are going to be spaced out like this. And since boron only ever forms 3 bonds, its molecular geometry is going to be trigonal planar. All of these bond angles will be 120 degrees like this. If I redraw BF3, I'm just moving it down so I can have a little more space. Hopefully you know which direction the dipole is going in because fluorine is the most electronegative element in the entire periodic table. Boron has an electronegativity of 2. Fluorine is double that, 4.0. That means we've got 3 dipoles, 1, 2, and 3. Now, can anybody give me a second guess as to whether this molecule is polar or not? Would this be polar or nonpolar? Yeah, this is a nonpolar molecule, so no dipole. This is a non-polar molecule. Okay, maybe I should rephrase that. Maybe I'll write it like this. No net dipole. Okay, we'll put here dipoles cancel because they're all pulling 120 degrees from each other, so they're all spread out perfectly evenly. And there we go. All right, Violet, is that one of my lines? We were just seeing if he was paying attention. Okay, this one of my lines, right? Whenever I make a mistake, I was just seeing if my students are paying attention. I say that all the time. All right, good. Okay, great. Well, practice makes perfect. Give another one a shot. The next one is carbonyl sulfide. It shows you, it even helps you out with this one. We kind of threw you a bone here and shows you the sequence of the atoms. So I'm not going to go over the Lewis structure in gross and am I running out of space? Oh, good gravy, Dion. Why don't I solve it up here? I'm kind of painting myself into a corner here, aren't I? Anyhow, I won't waste a lot of time on this one. Here's the order of the atoms. It looks like this: carbon, oxygen, sulfur. Oxygen and sulfur are in the same period. Now, in terms of electronegativity, oxygen has an electronegativity of 3.5, carbon has an electronegativity of 2.5, and sulfur has an electronegativity of 6. And so the dipole going in this direction is going to be much bigger than the little tiny dipole going in that direction. So let me ask you a question, not a trick question. Is carbonyl sulfide, is it a polar or a non-polar molecule? I'm not sure what yes means, Blake. Okay, polar, good. Okay, so polar, right? And the reason why it's polar is because this bond angle is 180 degrees, right? This is a linear molecule, but these dipoles aren't going to cancel. No freaking way. Okay, this dipole is much bigger, and therefore the net dipole is going to be in this direction. And so carbonyl sulfide is a polar molecule. Polar, or I don't know. In my notes, I wrote there's a dipole. Either way, and we'll put here net dipole. Okay. What do you think of polarity? Kind of cool, huh? Polarity is pretty darn cool. I think, Autumn, I think it's a good idea to memorize the electronegativities of, well, why don't we put it like this? Memorize EN value for hydrogen, boron, son of a gun, that's supposed to be the letter B, nitrogen, carbon, oxygen, chlorine, I don't know, chlorine maybe. That'll get you through most of what we're doing. Okay, if there's something else, I guess I'll give it to you. I never really thought about that a whole lot. Anyhow, you're thinking, that's your job, is to think about that. Here are the solutions. These are just Dr. Silverberg solutions. Anywho, here's the molecular geometry chart that I will give you. I will not have P and NP written on there. No. And I don't even like this whole NP and P thing. So the NP means nonpolar and the P means polar. I mean, I get it. I didn't write this in here. This is written in here by one of my colleagues, and I'm not throwing them under the bus, being like, I don't like it. But I like to rely on my wits on these things, okay? And there's a trap that students fall into sometimes, is this. There's kind of a general rule, and I mean, it's super general because there's plenty of exceptions, and you can see them in here, is that when you have lone pairs on the central atom, the molecule is usually polar. Okay, look. Lone pairs, lone pairs, lone pairs, lone pair, lone pair, lone pair, lone pair. So you can see that 1, 2, 3, 4, 5, 6, 7 times out of 10, the molecule is going to be polar if it's got lone pairs on the central atom. But you also see that there's 3 times when it's not. So that's kind of a rule of thumb, but that's one rule of thumb that this guy does not like. Okay, Mr. Dion does not like this rule of thumb. I like to just kind of draw the Lewis structure and evaluate it my own darn self before I start making any harsh judgments. Where was I? So again, I'll give you this table on your next exam, but I will not be writing any NPs and Ps on it. That was just something, an artifact put in there by a former a colleague of mine. Look, I wouldn't have included it in the slides if I didn't think it was useful. Okay, if you're learning, which you all are, if you're practicing this and you need to use this slide to help you, no problem. No problem. What else? Here's a fun slide. Every once in a while, not you guys, of course, I'm not talking about my general chemistry students, but sometimes I teach students who are grades obsessed. And there's nothing wrong with obsessing about your grades a little bit. That's a good thing. But I want you to also obsess about learning. Okay? Why am I here? Why am I learning this? And a good question to ask might be, and I'm sure you've all asked this question, is what's so important about molecular polarity, right? We just discussed, okay, this molecule is polar, water is polar, carbon tetrachloride wasn't polar, carbonyl sulfide was polar, carbon dioxide was not polar. What's the point, Mr. Dion? Why do we have to learn all this? Well, the reason why is because in order for you to understand and really understand things like physical properties, melting point, boiling point, refractive index, density, solubility, and reactivity, you have to understand molecular polarity. Okay, this is a big one. Students always, I always have a couple of students in general chemistry who are just so eager to get to the reactions. The first chapter we're discussing dimensional analysis, and they're like, when do we get to the explosions? Get me to the good stuff, Mr. Dion. Well, in order for you to understand, even explosions, you're going to have to understand molecular polarity to fully understand reactivity. Okay, general chemistry is a big class. It covers a wide variety of subjects inside chemistry. We cover a lot of different things. But I just want you to understand that I'm not just teaching you this to make your life miserable or because I'm obsessed with it and I want you to know. But no, it's important. It's really, really important. And I also have several students in this class who have told me that they're interested in taking organic chemistry in the future. And you can bet your bobby socks that in organic chemistry, molecular polarity will come up over and over and over. Okay? that's just me kind of going on a mini rant there, but I want you to understand that it's important. It's not just, Mr. Dion doing his thing and you have to follow along with what I like. No, 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 not at all. Let's we could start chapter 11 now, but who wants to it's Friday. Rebecca Black is celebrating somewhere with her, garbage bag full of money. Let's try who wants to try a couple questions just for fun? All right, practice problems. All right, Kenner is down. Okay, I got a bunch of students who want to try some practice problems. Look, again, I've said this to you guys before. Never be afraid to throw your hat in the ring on a practice problem in class. Okay, if you get it wrong, do I care? No. Okay, am I flagging you? Of course not. Okay, this is the place to get things wrong. So why don't we all give this one a try? I'm going to give you a second. We've talked about electron geometry and molecular geometry enough that I would like you to see if you can figure out the electron geometry, not molecular, the electron geometry for sulfur tetrafluoride. I'll give you a second. I see a lot of people are putting C. Okay, let's give it the old college try. Okay, let me maybe move this I don't know, down here. There we go. Okay, how many total valence electrons do we have in sulfur tetrafluoride? 6 from the sulfur. Fluorine has 7, and there's 4 of those. That's 28 plus 6. What's 28 plus 6? 34? We got 34 valence electrons. Sulfur, or fluorine rather, can only have 1 bond. Okay, and 3 lone pairs. So we'll fill all those up like that. Now I've used up 8 times 4, and 8 times 4 is 32 electrons. That means I'm going to put a pair of electrons on the central atom. That means that I've got 5 regions of electron density, and one of them is a lone pair. Now, if I have 5 regions of electron density, I think of my electron geometry being trigonal bipyramidal. And so the answer is D. Now, the molecular geometry, and this isn't asked for, but the molecular geometry would be seesaw, right? Because you'd have to take out or put one of the lone pair rather on the equatorial position like that. So again, electron geometry is trigonal bipyramidal, and molecular geometry would be seesaw. Does that help? Yes, sulfur can have an expanded shell because it's in the 3rd period. Anything below the 2nd period. Okay, well, let's try another one. Use Vesper theory to predict the electron geometry and the molecular geometry of phosphorus trichloride. I'll give this one a second for you to think about it. Oh, Jamil's got an answer. Jamil says D. You know what, Jamil? I'm just going to go with your answer. Okay. So phosphorus trichloride. Phosphorus has 5 valence electrons. Chlorine has 7. The 3 of those, 21 plus 5 is 26 electrons. Yes, there we go. Fix that up. So that means I'm going to have PCl3. I've used up 24 electrons. I got 2 electrons on the phosphorus. That means I've got 4 reds, and one of them is a lone pair. So my electron geometry is going to be tetrahedral. And what's my molecular geometry going to be? It's going to be this. So I'm going to have 1 chlorine in the plane of the board or the page or whatever, the screen. And I'll have another chlorine coming over here like this. And that is trigonal pyramidal. And so the answer is D, tetrahedral and trigonal pyramidal. Let's try another one. Selenium dioxide. It says, what's the molecular geometry of selenium dioxide? Did I even do this one? My notes are all over the place here. Oh, I did. Brienne says B. All right, let's give it a shot here. So selenium has a total of, how many valence electrons for selenium? 6, right? Because it's in group 6A. So you have 6 for selenium. Oxygen is in group 6A, so 6 times 2. So that's a total of 18 electrons. I'll start with my selenium. I'll put my oxygens at the end, like this. Now I've used up 16 electrons. I'll put 2 here. The oxygens don't have octets, and the selenium doesn't have an octet. I'll go through this one a little bit quicker. I'm going to erase both of these lone pairs on the ends, and I'll make double bonds like this. And now my oxygen have an octet. My selenium can expand its octet because selenium is in the 4th period. And so I've got 3 reds, 3 regions of electron density, and therefore I'm going to have a trigonal planar electron geometry. But what will my molecular geometry be? Well, it's going to look like this. I'll have my selenium and my oxygens will all want to get as far away from each other as possible. So my lone pair and my oxygens. And therefore, the bond angle overall is going to be bent or V-shaped. Bent is generally what we use. Okay, here we go. Which of the following molecules would be the most polar? Kind of an interesting question. I'll give you a second to think about it. Keep in mind, this is not a trick question. Mr. Dion is not into the trick question. Ouch. See, a bunch of people answered C. I think you're right, for sure, because it's got the most polar bond in it, right? Oxygen is the 2nd most electronegative element in the entire periodic table. It's got an electronegativity of 3.5. Carbon is 2.5. Nitrogen is only 3.0. And sulfur, we saw earlier, is 2.6. And so since this one has the most polar bond in it, it's going to be the most polar. And so C is the answer. C is the answer. Oh boy, now I get some big problems here. What question is this? 10.55. So I just pick some problems from the book here, I think. Yeah, give this one a little college try. Okay, so if we look at sulfur dichloride, fluorine, carbon disulfide, carbon tetrafluoride, and bromine chloride, which has bonds that are the most polar? Well, which molecules have a dipole moment? You know what we should do? we should start by drawing the Lewis structure and the molecular geometries of each one of these compounds. So let me move this. Oops, I didn't mean to do that. Okay, we'll start with SCl2. Sulfur has 6 valence electrons, chlorine has 7. There's 2 of those, so 14 plus 6 is 20 electrons. We put our sulfur in the middle. Chlorine is a halogen. It usually has 1 bond and 3 lone pairs. Now I've used up a total of 16 electrons. I put 2 on my sulfur. The chlorines have an octet. The sulfur has an octet. The sulfur has 4 regions of electron density. Therefore, the electron geometry is tetrahedral, but the molecular geometry would be bent. There's a number of ways I could draw this. I'll draw it with the 2 chlorines in the plane, like this, and then I'll draw a dash showing 1 lone pair in the back and a wedge. That looks like crap. A wedge, come on, Dion. And then a wedge coming out in front like this with the other lone pair. And so the molecular geometry here is bent. I've got a dipole going this way between the sulfur and the chlorine, like that. So overall, there is a net dipole in this molecule because I have 2 polar bonds and they don't cancel. So this definitely does have a dipole. So we'll put here dipole like that, and we'll just write it like this. Okay. And which one has bonds that are the most polar? Well, if I think about the electronegativity of sulfur and chlorine, sulfur has an electronegativity of 2.6, and chlorine has an electronegativity of around 3. And so the delta En is going to be around 0.4. Okay. Next, we'll look at fluorine. Why don't I do that one up here? Fluorine is a nonpolar molecule. Okay, so it's totally nonpolar. There's no dipole in it. There's no polar bonds, so that's not even in the running. Next, we'll look at CS2, carbon disulfide. So if I put the 2 sulfur atoms in here, like that, we said earlier on that sulfur has an electronegativity of 2.6, and carbon has an electronegativity of 2.5. So there are tiny, tiny dipoles going this way, but they cancel. So this is a nonpolar molecule, so no dipole in this molecule either. Okay, so no dipole. Dipole here, I'll put no dipole up here for fluorine. No dipole. What else do we have? Carbon tetrafluoride, so CF4. Carbon tetrafluoride should look like this. It's a tetrahedral molecule. It does have the most polar bonds, as you can probably tell right away, because carbon is 2.5 and fluorine has an electronegativity of 4.0. So my delta En is going to be 1.5. Overall, does this molecule have a dipole moment? Well, there's going to be 4 dipoles. There's a dipole going this way, this way, this way, and this way, but they all cancel out. And so this molecule has no dipole, even though it has the bonds that are going to be the most polar. So the answer is CF4. And then lastly, we'll take a look at bromine chloride. Yes, there's going to be a dipole in this molecule. It's a linear, it has no molecular geometry rather, but there is a dipole. Chlorine is more electronegative than bromine, not by much. Okay. And so there's a dipole, but it's going to be really small. And so we have by far the biggest dipole here. And the molecules that have a dipole moment, the ones that have a dipole moment, okay, are going to be SCl2, and bromine chloride, those two. So this is the last problem I have in the entire chapter. Which molecule in each pair has the greater dipole moment? Give the reason for your choice. SO2 or SO3. Again, do you want me to give you guys some time to try and figure these out, or do you want me to just solve them? If we were in class, I wouldn't ask your opinion, but since we're on Teams. Okay, so somebody says give us time. I'll give you 2 minutes to take a look at these. I'll even give you 4 minutes. And we'll come back and we'll take a look at all of them. All right, that's close enough to 4 minutes. That's the longest I've ever been silent in this class. Okay, let's give them a shot. So sulfur dioxide, SO2. This is A. SO2. Here's the Lewis structure for SO2. Okay, you can see that it has a bent geometry. We have 2 dipoles going this way, so overall our net dipole is going to be in this direction. SO3, on the other hand, sulfur trioxide, has a Lewis structure that looks like this. there are 3 dipoles, but since the molecular geometry is trigonoplanar, all 3 of those dipoles cancel. And so the most polar molecule is going to be SO2. In B, I have iodine chloride, and I have iodine chloride. We don't even have to look up the electronegativity values for these. We can just look at the trends. We know that electronegativity decreases going down a group. And so we are going to have a dipole in this direction from the iodine to the chlorine, but we know that dipole is going to be greater because the difference in electronegativity between iodine and chlorine will be greater because there's a farther distance between those 2 elements in group 7A. And so the answer here is IF. In C, we're looking at silicon tetrafluoride, which has a tetrahedral electron and molecular geometry, which looks something like this. There we go. All of those dipoles, which are certainly there, but all 4 of these dipoles are pulling in equal and opposite directions from that silicon, right? They're all pulling to the 4 corners of the tetrahedron, and therefore they all cancel out. Whereas in SF4, which we drew earlier on, we said that SF4 has the seesaw shape. And so it definitely has an overall dipole. We've got 2 dipoles that cancel on the ends like this, and yes, they do cancel, but I've got 2 dipoles pulling in this direction over here. And so the resultant is that the net dipole is going to be going in this direction, like that. And so the answer there is SF4. The next one is H2O versus H2S. They both have the exact same molecular geometry. I'll just draw them bent like this. You can put the lone pairs on dashes and wedges if you want. Book, sometimes he just draws a, an orbital like that. What else? We have the H2S molecule, which is also bent. And you can try to put the lone pairs on dashes and wedges. Are there polar bonds in here? Yes, but the polarity difference between oxygen and hydrogen is much greater than that between hydrogen and sulfur. And so the resultant dipole for H2O is going to be much bigger than the resultant dipole from H2S. So this is going to be the more polar molecule. Give me a thumbs up if you got those. Ka-ching. All right. Good.